So this experiment is testing the relationship between the resistors in a circuit and the voltage through each resistor, and how it changes for series and parallel circuits. The independent variable is the number of 100 ohm resistors and the type of circuit, and the dependent variable is the amount of voltage through each resistor. So my materials, I have these 5 100 ohm resistors cut into appropriate lengths. I have a breadboard, which I'll use to create the circuit. It's a bit easier than alligator clips. And then I have an Arduino board, which I will connect to my laptop with this wire to power the circuit with a voltage of 5 volts. I also have a few wires which I'll plug into the breadboard to create the circuit, and from the Arduino board to the breadboard to power the circuit. This is a multimeter, and I'll use it to measure the voltage. Slightly old, but it's the only one we had at our house. And these are the wires which will connect to the meter, the probes. And then that USB connects to my laptop, and it powers my Arduino board, which will act as the battery in this circuit. Then that Arduino board will connect to the breadboard using the 5 volt area, and that will act as the grounding wire. And the 5 volt connects to the positive, grounding wire connects to the negative. So for my procedure, first I'm going to create a series circuit on the breadboard using one 100 ohm resistor and 2 wires. So I put the resistor in from the positive to the middle. Then I use the wire to take the electricity across. And then I'll use another wire to take the electricity and connect it back to the negative wire, and then create the circuit. And once I connect this board to my laptop, there should be electricity running. Now if we measure the voltage, we get around 4.6 volts. And now let's disassemble it and create another circuit with 2 resistors this time. Connect the Arduino board to the computer, and now let's measure the voltage. It should be the same for both resistors since it's a series circuit and they're both the same type of resistors. So that, as you saw, was around 2.4 volts. Now let's add a resistor, and we shall only need to measure one resistor. In this case we get around 1.6 volts. Now let's disassemble it and add another resistor. There's 4 resistors at this point. And if we measure the voltage here, we get around 1.24 volts. And now with 5 resistors, we have 0.9 volts. Now let's try parallel. Both of the resistors have the same 4.6 volts. Total voltage of the circuit is running through them. Even if we add another branch, all 3 resistors still have 4.6 volts running through them. And we don't need to add more branches, but if we did, it would be the same. Now let's look at a diagram of the circuits we created. So we had a 5 volt battery, I guess you could call it, then 1 resistor, and then the wire connecting back to the 5 volt battery resistor was 100 ohms. That's what the circuit looked like. Now to calculate the voltage through that resistor, we can use V equals IR. In this case, our V is 5 volts. And our resistance, since we only have one resistor, is 100 ohms, which makes our current V over R. So I equals 5 over 100, which gets you 0.05 amps. And now we can plug that in to V equals IR to find the voltage across the individual 100 ohm resistor, and we get 5 volts. Now let's try the other circuit with 2 resistors with 100 ohms each. Calculation is the same except with 200 ohm resistance, so 5 over 200, 0.025, so 2.5 volts. With 3 resistors, 100 ohms each. Now we have a resistance of 300 ohms, so 5 over 300. We have a current of 0.0167, so 1.67 volts. Now we have 4 resistors, that's the diagram, which means a resistance of 400 ohms, which means that our current will be 0.0125 amps, so 1.25 volts. And with 5 resistors, we will have a resistance of 500 ohms. 5 over 500 is 0.01 amps, which is 1 volt across each resistor. Now for our parallel circuit, it looks like that. And now we'll do 1 over 100 plus 1 over 100, and the inverse of that, so we get 100 over 2, which is 50. So the total current is 5 over 50, which is 0.1, but since there's 2 branches, we're going to divide that by 2 to get 0.05 amps, and that times 100 gives us 5 volts through each resistor. With 3, we have 3 over 100, and the inverse of that, which is 100 over 3, so 33.33, so we get 0.015 amps, and that equals 5 volts. This is a series circuit data table. So as you can see, we have the voltage across the resistor, experimental, and theoretical. There is some difference. We'll calculate the percent error through these in a second. So to calculate percent error, it's the accepted minus the experimental over the accepted, the absolute value of that times 100. If we plug in the numbers correctly, we get a percent error of 8% for one resistor. And then you can see the percent errors for each resistor down below. Now if we do it for a parallel circuit data table, we have these values. They're all the same. Percent error for all of them is 8% because it's the same values. Now if we look at the graph, so for this graph, the x-axis is the number of resistors. The y-axis is the voltage through each resistor. This is for a series circuit right now. And as you can see, it's a relationship between resistance and voltage. So as the number of resistors increases, the voltage through each resistor decreases exponentially. Now this is the graph for a parallel circuit. And as you can see, they're both straight lines, because no matter the number of resistors, the voltage to each resistor in a parallel circuit will not increase or decrease, and XY axis are the same for this as well. And now this is the linearized graph, and it shows the same thing. The x-axis is the number of resistors, y-axis is the voltage to each resistor, and the line has a negative slope, which shows that as the number of resistors increases, the voltage across each resistor decreases. Now for our final discussion. So, first, our potential sources of error. So, the main source of error that we saw was that we expected the total voltage of the circuit to be 5 volts. However, it had a total voltage of 4.6 volts. That could be due to the internal resistance of the battery. So maybe the EMF was not 5 volts, it was 4.6 volts. The experimental design could be improved to reduce that error if we already knew the internal resistance and we accounted for that in our calculations. We would have very less percent error. So one of the main limitations experienced due to being constrained to household materials, the voltmeter was more of an older version, and that meant that the values which were measured may not have been as accurate as they could have been with a digital voltmeter. Another thing was the voltmeter, or the multimeter, was not capable of measuring very high values of current, and that meant that it could not measure the amount of current which was flowing through our circuit. So the relationship between the independent and the dependent variables, the independent variable was the number of resistors, and the dependent variable was the voltage across each resistor. So in a series circuit, as the number of resistors increases, the overall current going through the circuit will decrease, which means that the voltage across each resistor will also decrease. However, in a parallel circuit, no matter the number of resistors, the voltage across each resistor remains the same.